Hello, this is video number 2 of section 5.2. This video we want to answer the very important question of which bear is best. No, sorry. What other ways do we have to determine, or how can we determine, if two matrices A and B have the same eigenvalues? So we know one way, right? Certainly if they have the same characteristic polynomial, then A and B will have the same eigenvalues, right? So we learned in last video that the eigenvalues of a matrix are completely determined by the roots of its characteristic polynomial. And so if we can show that two matrices have identical characteristic polynomials, then certainly their eigenvalues will be the same. And you wouldn't have to go too far to find an example of two matrices that were definitely not equal that had the same characteristic polynomials. So a very quick example might be something like this, where each of these matrices is upper triangular, and so they would actually each have the same characteristic polynomial of lambda minus 1 times lambda minus 2, even though this upper right entries are different, right? And so here you could see that the matrices are different, but they have the same characteristic polynomial, meaning these two distinct matrices have the same eigenvalues. So we want to talk about sort of another way of determining, and sometimes an easier way of determining, when two matrices have the same eigenvalues. This will be used a lot, especially next section, when we introduce a process called diagonalization. So, also, grizzly bear is best. I guess since I'm from California, I have to say grizzly bear. Anyways, we say that two n by n matrices A and B are similar if there is an invertible matrix P such that A is equal to P times B times P inverse, or equivalently, if this is true, then B is equal to P inverse times A times P. And of course, you can get from here to here or from here to here by just multiplying both sides on either side of the equation by P or P inverse, right? So if I multiplied by P inverse on the left, P inverse on the right, I'd get to here. And so each of these things is equivalent. However, do note the order that P and P inverse come in this similarity transformation is what we call these equations, does matter, right? So if P is on the left side of B here, then P inverse has to be on the left side of A in this equivalent equation. Well, we actually know that if two matrices are similar, and we'll prove this as a theorem, and B are similar, well, then their characteristic polynomials are the same. And since their characteristic polynomials are the same, they also have the same eigenvalues. So like with the last few proofs, this proof is relatively short and I believe very doable. And so I would definitely encourage you to pause, try to work through the outline of the proof I have. But I'll go ahead and just start proving it here. So our goal in proving this theorem is to show that if A and B are similar, they have the same characteristic polynomial. So our goal is to show that the determinant of B minus lambda times I is equal to the determinant of A minus lambda times I. And this is for any arbitrary variable lambda here. So we're allowing lambda to just be sort of a variable. And much like in these proofs, we have to start with something we know. So we know that B is equal to P inverse times A times P. Right? And we could use either one of these, so you could do this sort of in the alternative direction with A and B, but we'll just write out this. And we know this because A and B are similar from the definition of similar. All right, so this implies, certainly, that B minus lambda I is equal to P inverse times A times P minus lambda I. Because all I did here was just subtract lambda I from each side of the equation. Right? So I'm allowed to do that. I can subtract the same thing on either side. This is kind of the cool trick. So since so I'll do this step here and then explain how I know I can do this. I can actually multiply both sides of this second term by P inverse and P. So the reason I can do that is because notice here I'm allowed to multiply. So this is sort of one of those tricks in math where we're multiplying by, well, we're not really multiplying by 1, but we're multiplying by the identity matrix in just sort of a clever way. So what I'm doing here, I can multiply lambda times I by P inverse times P, because this here is just the identity matrix, right? And so again, multiplying the identity matrix times any matrix doesn't actually change that matrix. So I'm not doing anything to change the matrix lambda I here. But remember, the identity matrix commutes with every matrix of the same dimension, right? The identity matrix is the same if I multiply it on the right or the left. So what I can do, and of course any scalar can just factor out or factor in, I can actually take this P inverse and bring it out to the left here. Well, this implies now that B minus lambda times I is equal to P inverse times A minus lambda I times P. And I can do that because I can factor each of these P inverses out on the left and factor each of these P inverses out on the right. Well, this means that the determinant of both sides of this equation are equal. But notice this is 1 matrix, 2 matrix, 3 matrix. So by the multiplicative property of determinants, I can now multiply by determinant P inverse times the determinant of this middle matrix times the determinant of P. But remember, this is just a real number. This is just a real number. This is just a real number. So all of these values commute. And remember, we proved that the determinant of P and P inverses are multiplicative inverses of each other, right? That is, if this is equal to x, then this is equal to 1 over x. And so this whole right-hand side of the equation is actually just equal to the determinant of lambda times I. So this last line here proves the sort of goal we were working towards, that the determinant of B minus lambda I is equal to the determinant of A minus lambda I. And that means that the characteristic polynomials of A and B are the same, meaning they have the same eigenvalues. So notice here, the matrix P doesn't really matter. The matrix P in this proof is basically just an invertible matrix, right? And so all that we need to do to show that two matrices are similar is just find an invertible matrix that sort of gives us this similarity transformation. And so at the end of this, we're going to look at one example that sort of might shed some light on why we care about determining if two matrices are similar. And this will also sort of be a precursor to section 5.3. All right, but before we move on, I want to go over a very cautionary example. Because while two matrices being similar implies that their eigenvalues are the same, there are many, many examples of matrices with the same eigenvalues that are not similar. So my favorite example and I'll put this in all caps, so you know I'm being serious. My favorite example of this phenomenon are these two matrices. Mostly just because the zero matrix is always my favorite example because it tends to be easier to work with. So we've got the following two matrices, A and B. They each have exactly one eigenvalue, right? Because each of these matrices is technically upper triangular, and their one eigenvalue is 0. And so each of these has eigenvalue 0 with multiplicity 2. But notice that these two matrices cannot possibly be similar. So despite having, and actually even on top of that, we can say the exact same characteristic polynomial of lambda squared, A and B are not similar. So despite having the exact same characteristic polynomial, they're not similar. Why is that? Well, if they were, well, even beyond that, let P be any invertible matrix, right? And certainly if they were, we should be able to find some invertible matrix which transforms A into B. Well, P inverse times A times P is equal to P inverse times the zero matrix times P, but anything times the zero matrix is the zero matrix, right? And so no amount of multiplying A by any matrix is ever going to produce a 1 out of thin air. Right? There's nothing you can do to 0, at least multiplicative-wise, that will ever turn 0 into any non-zero number. And so in this way, well, through this example, you can see just because two matrices have the same eigenvalues does not mean they are similar. The other way around, great. If you can show that two matrices are similar, they have the same characteristic polynomial, they have the same eigenvalues, not the other way around. Just because they have the same characteristic polynomial and the same eigenvalues does not mean they are similar. This is maybe the most straightforward example because it's so easy to show these matrices are not similar, but there are many, 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 many examples just like this one. So be really careful about that. I know that when I work through linear algebra problems and I want to show that two matrices are similar and I see that they have the same eigenvalues, there's always this part of me which wants to think, oh, you know, I've shown they're similar, but they're not. It's just, you know, definitely an easy thing to forget or an easy mistake to make. So just really sort of have that like cautionary note written somewhere close when you're working on these problems. All right, so I want to look at an example now. We're going to let A be the following matrix: negative 21, 15, negative 40, 28. And we'll let B be the matrix 4, 0, 2, 3. And we want to find the eigenvalues of A. And so, like I said, if you want to calculate the determinant of this, you know, factor things, you know, that's fine. But we also know that if P is equal to the following matrix, 1, 0, 2, 1, and, well, then we know that P inverse is equal to 1, 0, 1, negative 2, then it's not hard to verify that P inverse times A times P is actually equal to B. And so it turns out that just knowing this now is going to make finding the eigenvalues of A much easier, because this means A and B have the same eigenvalues. Oh, and why is that nice? Well, we know the eigenvalues of B because it is an upper triangular matrix. And that means we know the eigenvalues of A. So I just sort of wanted to briefly give this example because it really does show, okay, why did we define this and why do we care? That, if you can show two matrices are similar, well, certainly, these two matrices being similar, meaning they have the same eigenvalues. As we'll see, there are a lot of other things properties, I guess you could say, that similar matrices possess that we'll learn. And with those sort of shared properties, there's a lot of times where we want to know the eigenvalues of a matrix. And so if we can sort of transform it into a matrix whose eigenvalues are either easier to find or easier to see or easier to work with, right? That we can transform it into this matrix where just looking at B, we know what its eigenvalues are. There's a lot of utility in that. And so this is sort of why similarity transformations in this way are so useful and so nice, because we can take a matrix that its eigenvalues would be very difficult to find and turn it into a matrix whose eigenvalues are easy to find. And of course, if we were to be looking at this problem maybe in an applied setting, maybe we wouldn't know P and P inverse, right? So here it was certainly a little more straightforward because I gave you P and, well, I didn't even, ask to verify or want to spend too much time verifying that this equation was satisfied. I did verify it on my own separately, but, as you can see, it made the problem of finding the eigenvalues of A easier, and as we'll see moving forward, there are a lot of instances where having a similarity transformation like this will make things easier for us. Especially looking at, again, we'll go back to looking at square matrices as linear transformations, and we'll see that these similarity transformations can be quite useful in that regard as well. And this is what we're sort of going to be talking about next section when we talk about diagonalization. So anyways, I want to end with one more warning, and then we'll be done with this video. So the last warning, and this is actually another, it's kind of funny. This is one of those mistakes that I felt myself making a lot and that I'd kind of forgotten about, and then the book mentions it. And I was like, oh yeah, I did want to do that a lot as well. And so I'll give you one more example, that row equivalence does not equal similarity. And actually, many row equivalent matrices don't even have the same eigenvalues. So not only do we not guarantee similarity between row equivalent matrices, oftentimes row operations will specifically change the eigenvalues of a matrix. And to see that, we can consider the two 2x2 matrices, A and B. So here A has eigenvalues lambda 1 equals 2, lambda 2 equals 3. B has a single eigenvalue with multiplicity 2 of lambda 1 equals 1. And it would not be hard to see that you could row reduce A to B, right? In a couple row reduction steps, you could easily get from A to B. But notice these two matrices don't even have the same eigenvalues, or they don't even share one eigenvalue. And so in general, also, row operations change the eigenvalues of a matrix. So be very, very careful with that as well moving forward. That, you know, if we're looking at eigenvalues or wanting to study the eigenvalues of a matrix, we're often not able to do row operations with that matrix. Of course, the one time where we'll kind of bring row operations in is solving for eigenvectors, but in terms of eigenvalues, the row operations will often change the eigenvalues of a matrix. So anyways, that wraps up this video. Like I said, at least next video, I haven't yet completely outlined it yet, because I think this pretty much gets us through all of the material in this section. I want to do at least one example where we kind of work through the whole process of finding an eigenvector, finding eigenvalues, finding eigenvectors. And so we'll at least do that, but I want to look through the problems and see if there's maybe anything else. But anyways, thanks for watching.